Sorry for the small issue that going to be fixed, but now we are going to hear Abhishek. We're going to talk about MELL proofnets without nonsense.
Oh, thank you. It's my first day of work this year, and it's a great start of term. So thanks everyone for the talks. So this is work in progress with Kostia Chardonnet from Bologna. Right now he's moving to Nossi. So we are taking a look into MELL proofnets as if people haven't done that already. So my idea is that I'll talk about MELL proofnets and the discontents that it throws up, and then I'll introduce something which we call infinitary MELL, and I'll talk about the proofnets that these throw up. So you'll already see that this has nothing to do with game semantics, and I think somewhere in the distant future there could be a connection. So you have to kind of imagine the game semantics somewhere. Right. So let's talk about MELL proofnets. So why do we do proofnets? So this is like the sales pitch of proofnets. There are two important things here. First is the Hilbert's 24th problem, which is when are two proofs the same? And another thing is about the annoying commutation steps anytime you do a cut elimination proof in sequent calculus. So consider these two proofs on the left. Just computed the sequence of application of the rules, and computationally they should be similar objects. So we should have a paradigm to say immediately that they are the same objects, and that's what proofnets gives you. On the other hand, you have these two proofs which kind of look very similar, but they are very different computationally, and indeed they have very different proofnets. So jumping ahead without introducing proofnets, in the world of proofnets you only have key steps of cut elimination. So every step is you're doing some sort of computation. So these are the rules of cut elimination in MELL proofnets, multiplicative linear logic proofnets. So what are MELL proofnets? So first I'll establish the language. You have some atoms, no units, tensor, which is like the multiplicative conjunction, par, the multiplicative disjunction, and the ability to duplicate and weaken stuff, so to copy and to delete, which is the question mark, and then you have the bang. So at this point I gave up on ticks and started drawing. This is the promotion box. But so you have axioms, cuts, so nodes for tensors and pars. They look the same, but they will be distinguished later. You have weakening, which tells you that you don't need to use the question mark anymore. Dereliction, which kind of takes away the power to copy and delete. And then contraction, which allows you to copy. And the promotion is this kind of sequential thing which loses the bang loses its power, and it has to be done within a context of a question mark. So we ensure soundness by a correctness condition so that we avoid nets which does not make sense. Girard called this particular net a vacuous circle. Anyway, so the point is that these promotion boxes are a bit annoying. It the two good things which I mentioned about MLL proofnets, they kind of disappear when you talk about MELL proofnets. So first of all, you lose the sort of canonicity, the fact that if you have computationally irrelevant things, they are the same proofnets. Because here, you do first a contraction and then promotion, but it does not really matter in which order you do them, but they still have two different proofnets, which is not something we would like to have. And this only happens because the promotion adds an extra layer of sequentiality. On the other hand, cut elimination becomes non-local. So if you have a cut with a promotion and a weakening, it deletes a box, which is not a local step of cut elimination, but one huge step of cut elimination. A huge step of computation as well. So what have we tried so far? By we, I don't mean I, the editorial we, I mean we as a community. So there have been, people have proposed lightweight proofnets and some sort of jumping boxes, what is known as. So like there are various methods of getting rid of the boxes, and each of them have their own computational interpretation. So these lightweight proofnets were basically based on some sort of interaction net formalism, and basically the nodes carried some indices, numerical indices, which were basically data telling you how deep you are inside a box. And the jumping boxes also are sort of similar mechanism to get rid of the box, but using a more graphical notion. So this brings me to infinitary MELL, which I want to introduce. So it was already known, Girard already said this, that you can look at the exponentials and approximate them during a particular use of that exponentials, and you can get a purely linear proof. What he was getting at was that exponentials can be seen as fixed point formulas, and you can also write this as a recursive equation, so which gives you the fixed point formula formulation. And we have seen the success of adding fixed points to linear logic, and this has been a tradition of work from David Ball, Dale Miller, Amina Dumain, and so on. And so I want to exploit the things they have done to understand whether this new way of looking at exponentials can give us something interesting on the proofnets. So, non-exponential rules stay the same. I just introduce the new rules for the exponentials. So now you have a non-well-founded system. So the proofs are defined co-inductively. So pre-proof is co-inductive generated by the rules of MELL. And you have the following rules for the exponentials. So for question mark, they are still the same. You have weakening, dereliction, and contraction. For the bang, you literally have the rule which you would have if you unfolded this fixed point. So it's a fixed point unfolding rule for the bang. It has three premises, and in the last premise you see the bang repeating. So there is a possibility of doing this bang infinitely, on working on this bang infinitely often. So a pre-proof is called progressing if in every branch the bang rule occurs infinitely often, and a progressing pre-proof is a proof. So we would like to impose this progressing condition, because otherwise we could prove bottom. We wouldn't like that. And using this sequence system, I would like to go to the corresponding proofnet formalism. So let's see some properties of this new way of looking at exponentials. So first of all, you have canonicity. So if you know, in usual MELL, you do not have canonicity of the exponential. So in particular, if you add another operator with the same rules, you cannot show that they are isomorphic. But here, since you do not apply the bang rule in any context, you get get back canonicity. And by the way, this shows that it is a proof because indeed the bang occurs infinitely often in this proof. But it is not exactly MELL because it is not provably equivalent to MELL. We can come up with a sequent which is provable in this infinitary MELL but not in MELL. It is a result due to Anupam Das, which he communicated through a mail chain for some reason. And it also does not satisfy the Sealy isomorphism. So, but I would like to see, nevertheless, what sort of proof nets they throw up and what sort of interesting computations we can do with that. So let's get into MELL proof nets. So I'll be very hand-wavy here. So basically, an MELL proof net is a sequence of finite proof nets. And the sequence is such that you can kind of plug them together in a coherent way. So they're compatible in some way, jigsaw puzzles. And they get bigger and bigger and bigger. So in some way, it's like approximants of a fixed point. And we have to introduce 3 new sorts of nodes. So first we need a generalized axiom so that we can expand this generalized axiom to kind of increase in size the approximants. And then we need question mark and bang nodes, obviously, which have each of them have 3 premises depending on, and they are exactly like the fixed point formulation of that. And the question mark and the bang, they act like with and plus. So basically, a MELL proof net is an infinite sequence of MAL proof nets. So I throw in some additive behavior in that. Immediately, we get that cut elimination is local. And also, we get rid of the boxes. But these are just 2 superficial observations I made. I don't know, basically that's why I want to talk to you. Basically, I want to understand what sort of computation we can do with this. So I did some preliminary things. So first of all, I checked that we can still do promotion. So this is also an example of how to look at these proof nets. So imagine you have a proof net with doors bang and bang gamma and A, and you want to define the promotion. So you have to give infinite sequence of proof nets, and I give it by induction. And so Ri plus 1 uses this R once and has Ri's as objects inside it. And so this question mark node here acts as a plus. And so this is like in the tradition of MAL proof nets, you use some of the premises and you don't use some of the premises, that sort of thing. So now we can translate simply type lambda calculus in this formalism. So if you have a term which is typed by A arrow B and a term typed by N of type A, then you can get a term Mn of type P. Basically, this is the usual translation of simply type lambda calculus into MELL. But now that we know how to do a promotion, as we saw here, we can basically translate simply type lambda calculus into our setting. And so that's basically where I'm at. So we introduce MELL, infinitary MELL, and we introduce its proof nets. Turns out exponentials in this setting are canonical, and we introduce a notion of nets that avoid the use of promotion boxes, and consequently we get that cut elimination is local. But what I would like further is what is really the computational meaning of using these objects, and in particular, can we translate more expressive calculi, I was thinking like the resource calculi, and then we can make this could be a GALOP talk because we know that Taylor expansion is game semantics. And then I was thinking, I don't know what is the computational implication of the lack of the Seeley isomorphism. So some people have me to look into this paper by Booth, which is on non-uniformity. It's a very hard paper to read, so if you have some recommendation. Finally, I would like to see what sort of geometry is thrown out by this new formalism and what sort of paths we get in this new way of living. So, thank you. Yep, yeah.
Thank you. So when you say that the Seeley isomorphism doesn't hold, does that mean that one of the directions is not provable, or that it's not an isomorphism?
It's provable, but it's not an isomorphism.
Okay, thanks.
Other questions?
Thank you. Wait, I forgot my question now. Yes, so can we have another look at the construction for promotion?
Yeah, sure.
Is it an infinite proof net, or is it
No, so this is a bit orthogonal to what I did in my PhD actually. I worked on adding linear fixed points to MLL and looking at proof nets for that, and they were really infinite objects, so they were infinite graphs, but they were really complicated to work with. And now if I work in that formalism here, it becomes just unbearable because you have to add this extra additive layer on top of that. So instead what I do is I thought we could get away with just working with approximants, and so each of these approximants are finite proof nets.
But what about the correctness condition? Because wasn't the correctness condition something about infinite branches?
Yes, so we could, since we don't have general fixed points, we could get away with not having that big correctness condition on infinite branches. And if each approximant is correct, we get the whole thing is correct.
Okay, thanks.
Okay, so let's thank Abhishek again.
Thank you.